Yes, class. Now, Bernoulli's theorem and one Torricelli's theorem, these two topics are left. So most of the portions of mechanical properties of fluids are also completed. So see, few energies I wanted to discuss with you, which we have already studied, but in terms of fluid, we haven't. Potential energy of a body is mgh, that we know. Now see, suppose this is a container. This container, this is filled with fluid. Mass is m, and this is raised to the ground by height h. Ground is this. All right. Now see, what is the potential energy per unit mass? Why we are studying this separately? Because when we'll combine the entire Bernoulli's theorem, we'll be using it. So potential energy per unit mass, that will be mgh divided by m. So mm will be cancelled, which is equal to gh. All right. Now, and if I say potential energy per unit volume, this is equal to mgh by v, or see, mass by volume. What can you write mass by volume? What is mass by volume? Yes, Sarah. Alia.
Rho.
Rho, density. Very good, Alia. This is density. Mass by volume is density. So this is rho gh. Now let's keep it aside. This we'll be using, but let us keep it aside. Let's bring kinetic energy. So kinetic energy, you know, it's half mv square. So if I say kinetic energy per unit mass, so what will it be? This is kinetic energy per unit mass will be this divided by m. Mm will be cancelled. We'll have v square by 2. Kinetic energy per unit volume, half mv square by volume. Volume is capital V, velocity small v. Please be clear. So again, mass by volume is rightly answered by Alia. This will become half rho v square. Fine. Let us keep this also aside. So both of these energies you are already aware of. Now there is one more energy which is known as pressure energy. It means basically pressure of the liquid. So pressure energy is the work done by the pressure. So pressure energy is equal to P delta V. Why P delta V? Okay, we haven't done thermodynamics, no. In the batch which is going on, we'll be completing that also. This is basically change in the work done. This is change in work done. Just remember it for now. When we'll jump to thermodynamics, we'll complete. All right. Yes, Sarah, you're not attending the classes also. Anyway, this is pressure energy. Pressure exerted by the liquid column. This is basically pressure exerted by the liquid column. Fine. So these are the three energies we have: kinetic energy, potential energy, and pressure energy. So when a fluid is there, suppose this fluid is there, particles are moving, so that's why they are having kinetic energy. They are exerting forces on each other, so they are having potential energy also. Fine. And there is a pressure exerted by the entire liquid column, so there is pressure energy also. What is the meaning of Bernoulli's theorem? What is Bernoulli's theorem? Bernoulli's theorem basically says that, first understand, then you can write it down. It says that total energy per unit volume, this will always remain constant. What is meant by total energy? You have three energies which come under total energy. Which all energies we have studied right now? Potential energy, kinetic energy, and the pressure energy, which we'll denoted by V or P you can use. These three energies. So per unit volume is also there. So we have divided them by per unit volume. What is potential energy per unit volume? Rho GH. Rho GH plus. Then you have kinetic energy per unit volume. It's half rho V square. This is half rho V square. V is velocity. And then we have pressure energy. I'm writing it as P. This will always remain constant. And this is what is meant by Bernoulli's theorem. So what is Bernoulli's theorem? Bernoulli's theorem says that It states that for the steady flow of an ideal liquid, the total energy means sum of pressure energy, then second, potential energy, third, kinetic energy. This is important. Per unit volume remains constant throughout the flow. The importance of this theorem lies in the fact that it can be used to determine the variation of pressure in liquids as the function of velocity of the liquid and the elevation of the pipe through which the liquid is flowing. All right. So these are the types of energies and the entire Bernoulli's theorem. Now we have a derivation also for this purpose. Derivation also we have that I'll discuss. First, write this down. Then I'll discuss the derivation. See, for the derivation of Bernoulli's theorem, I'll consider a pipe, but I will take both the ends different. See, here we had taken this end no, from the ground. So what will I do? I'll take a pipe in such a manner so that I'll get two different height. So suppose this is the shape which I have taken. Very narrower and getting broader towards the end. Like this. All right. Now see, area here is A1, velocity is V1. Let's say this is the ground level. Height is H1, pressure here is P1, this is one end, and diameter is D1. This is second end. Here everything is different. Height is H2, pressure is P2, diameter is D2, area is V2, velocity is V2, diameter D2 I have taken. Now see, fluid will start moving from here. Fluid will start moving from here. Now see, when I'll calculate the force at first end, pressure, you know, pressure is equal to force by area. So force is equal to pressure into area. Now, what is the work done? Work done is equal to force into distance. Here, the distance is the diameter. All right. Or let's take D1 only as a distance only. Here, I've taken it as D1. No, so let's forget diameter. Whenever diameter will be used, we'll write it as something else. Distance that is traveled by the water is D1. So what is work done 1? Value or put the value of force from this equation, from this. So this will be P1, A1, D1. Fine. Now distance. If velocity is V1, distance is D1, time is, let's say time is T. Time will be the same. There is no time difference. So how can we relate them? By the equation of velocity. V1 is equal to D1 by T. So what is D1 is equal to? V1 into T. So final work done will be equal to P1, A1, V1 into T. Fine. Similarly, when we write the work done at N2, it will be P2, A2, V2 into T2. Now see, here it is in opposite direction, right? This was coming from this side. Force was acting and pressure was being exerted on this side. Here this is coming out. So distance was the same. Here distance and displacement both are different. So that's why we are having this negative sign. Now when we are calculating the net work done, if we say net work done, this will be equal to P1, A1, V1T minus P2, A2, V2T. Net work done. Now, whatever fluid has entered this first stage, that will only leave. So the fluid that has entered at end 1, so volume of this fluid is equal to volume of this fluid. Now look, so we can say volume of fluid entering at end 1 in time t is equal to volume of fluid leaving the tube at end 2 at time t. So what is the volume of fluid? A1, area into distance, and distance is velocity into time. Clear? See, volume is equal to area into distance. And further distance is written as velocity into time. This is clear how this is written A1, V1, T. Similarly, this is equal to A2, V2, T. Fine. Here, TT will be cancelled if we write the same. Or let's write it as different only for the time. Now, look, when we're talking about work done, P1 delta V minus P2 delta V, we can take P1 minus P2 common into delta V. This is the potential energy. Remember, P delta V. And what about the kinetic energy? This is half M V2 square minus half M V1 square. Potential energy mgh2 minus mgh1. Everything that we have studied. What is pressure energy? P2 delta V minus P1 delta V. And what is the total work done? Total work done is basically sum of kinetic energy acting plus potential energy acting in your system. So total energy, we can write it as P1 minus P2 delta V. This is work done. P delta V. This we haven't discussed. We will discuss this in thermodynamics. P delta V. So half mv2 square minus half mv1 square plus mgh2 minus mgh1. So this we can write this as, let's separate this. Let's multiply this. P1 delta V minus P2 delta V is equal to half mv2 square minus half mv1 square plus mgh2 minus mgh1. Fine. This is how we can write this. Now look, class. What is P1? PV1. This is the first pressure energy, right? Or let me do one thing. Let me rearrange the terms. Wait. Finally, let me write down the final answer, which will come. I'm just rearranging the terms. Till here, it's clear how we have reached here. It's lengthy, you can write it down also. Now see, I'm just rearranging the terms. P1 delta V. From here, I'm bringing this. So it will become plus half mv1 square. And I'm bringing this also. Plus mgh1 is equal to, I'm bringing it here. P2 delta V. This was already there. Half mv2 square plus this mgh2. What have we obtained? This is initial pressure energy. This is initial kinetic energy. This is an initial potential energy. This is final pressure energy. This is final kinetic energy. This is final potential energy. What was our equation initially with which we have started? Pressure energy plus kinetic energy plus potential energy, all will be constant. That's the difference that will come. Just in case this was the maximum extreme condition I assumed, where height was also different, shape was also irregular. In case you have such type of normal simple pipe having both the height same, you will not have potential energy component there. Simply use P1 plus half rho V1 square is equal to constant. That's it. No need to use potential energy component because no difference in potential energy, that will be cancelled. If height is same, see in this equation, if height becomes same, they both will be cancelled. So just use this. If you have horizontal pipe condition, write down the derivation of Bernoulli's theorem, and this is very important. Bernoulli's theorem. Class, the screen is visible to you? Sorry, my internet, actually Wi-Fi got disconnected. I hope now I'm audible also. My screen is also visible. This slide you have written? Should I scroll? Yes, no, what?
Yes, ma'am. Yes, ma'am.
Okay. Yes, class, let's discuss this question. It says that water is flowing through two horizontal pipes of different diameters which are connected together. In the first pipe, speed of water is 4 meter per second, pressure is 2 into 10 to the power 4 Newton per meter square. Now, diameters of pipe, you have to calculate speed and pressure of water in the second pipe. See, first apply the Bernoulli's theorem's equation. We have studied that P1 plus half rho V1 square is equal to P2 plus half P2 plus half rho V2 square. So what all things do we have from the question? P1 is given as 2 into 10 to the power 4. Rho is given as 1000. Velocity is given as 4 meter per second. So when we'll put 2 into 10 to the power 4, fine, see, this is the pressure. So P1 plus half, what is rho? 1000 V1 square, that is 4 into square, is equal to P2, we do not know, plus half into 1000 into V2 square, we don't know what's the velocity. But one equation we have studied. What was equation of continuity, class? Remember, I told you that equation of continuity. A1 V1 is equal to A2 V2. This we will use. You have seen, we are given with diameters. The reason is that pi d1 by 2 whole square v1 is equal to pi d2 by 2 whole square v2. Fine, 4 will be cancelled, pi will be cancelled, this will be cancelled. So we are left with, what is the value? V2 then? d1 square into v1 divided by d2 square. What is V2? 9 into 4 by 36, which is equal to, again, this is 1 meter per second. Now you know this is 1. You can find out the value of P2. If we solve this, this will be 2. Here we have 4, 16, 16 plus 2, then from here 2. So 4, 2, 2, 8, then these 3, 0, no? 2, 8, 0. Please cross check later also. Is equal to P2 plus half into 1000. Why? Because velocity is 1 square. So this is 500. So P2 will be 27500 pascals. That is it. Using equation of continuity, we have found out velocity. Using Bernoulli's theorem, we have substituted the value to get the pressure. These were the unknown quantities. Write it down.
Okay, go up, ma'am.
Now, there are few applications of Bernoulli's theorem. See, first application is aerofoil lift. Aerofoil lift means this is the shape of aerofoil, like this streamlined shape. Base is a little flattened, upper is a little curved. So what happens when this is moving? It tears up the fluid because of its shape. All right. So here what happens? Pressure is being applied from this side as well. Pressure is being applied from this side as well. So here at the upward surface, pressure is less, so velocity increases. See, let's say this is P2. Let's say P2 is greater than P1. All right, so below is pressure is more. So since the pressure is more, we have the velocity less. Pressure is more, we have velocity less. So what happens? As a result, the net pressure when you calculate, net pressure becomes P2 minus P1. So the force becomes P2 minus P1 into area. So see, an aerofoil is shaped so that air flows faster along the top surface than the lower one. According to Bernoulli's theorem, we have the inverse relation of pressure and velocity. In order to increase over this sides, why? If this pressure is more, P1 is more, it will push it down. If P2 is greater than P1, then only it will pull it up, and we want it to move. That's why pressure is made greater on the bottom side. So an aerofoil is shaped so that air flows faster along the top surface than the lower one. Fine. Pressure of air below is greater than above, and this pressure difference creates an upward force, which is known as the dynamic lift. So this can be asked. Similarly, one is the aerosol sprays which are present, or atomizer, or normal simply sprays or perfumes which are present. In these, no, atomizers or sprays, you have a tube which is connected to a bulb. These are just the applications. If applications are asked, you can explain these. So bulb is there, which is connected to a thin tube. This is contained in a container which lets air pass through it and leading to a very narrow tube. This has a bulb. Here is the pump which you press up. So in the bulb region, here the pressure is less, so that velocity increases. So what happens when the velocity increases? Particles move here and then travel and finally come out in the form of sprays. So see, when the bulb in the atomizer is squeezed, air rushes through the narrow neck of atomizer. This reduces the pressure in the narrow channel. So that atmospheric pressure pushes the perfume up the tube, leading to the narrow channel. Then the perfume is then dispersed into fine spray of droplets. This is one more application. One last application that we have of Bernoulli's is blowing off the roof in the storm. See, those roofs which are made not of the cemented materials and all, the light roofs which we have, when the storm passes. So what happens here in the upper region, this side, the pressure decreases and velocity increases, which results into getting swiped off. Like if this is the house, the roof moves up. So see, when wind flows with a high velocity above the roof of a house, it causes lowering of the pressure. However, pressure below the roof is still atmospheric. Below the roof here, it is still atmospheric. So if the wind blows fast enough, internal pressure can blow the roof off. So these are the applications of Bernoulli's through which actual applications occur. Write these down quickly. Till here I'll stop. Now last portion is only left. One more class I'll need and I'll complete this. So all those who have completed, you can start leaving one by one.